This video will give an overview of supported formats from test and CAE files and how to import and export them in Altair Compose. So let's start explaining about general input in Compose. There are some main categories of files that are commonly used in signal processing workflows, and each one has a more appropriate function to import data. Compose is able to read inputs of multiple formats like Excel-compatible files such as CSV or XLX, MAT files which have a container-like format and stores variables of all data types supported by Compose, test and CAE files which will be covered shortly, and finally other formats like binary, delimited files, text files, and images. As we are primarily focused on signal processing in this video, test and CAE files will be our main interest. Now let's focus on test and CAE files. Compose allows direct reading of numerous CAE and test data formats, time and frequency based. And regarding CAE, we support files from multiple solvers of finite element method, computational fluid dynamics, and multi-body systems. And regarding tests, we support formats such as UNV, ISO, ASCII, CSV, and others. And the main takeaway is that no translators or converters are required. There are four main functions for this purpose: read vector builder, read vector, read mode vectors, and read CAE, which will be explained in a minute. It's also possible to write a new CAE file using create ABF file function, which creates an Altair binary format file, and ABF stands for Altair binary format, and create H3D file, which is the main standard used by Altair within its finite element solvers. And as a good practice, close the file using release data to release from memory only what's been read, and release file info to release from memory the file as a whole. Let's discover more details about the ways to read test and CAE files. Switching to Compose's interface, the first one is Read Vector Builder, a utility tool that reads test and CAE result files and helps to create the right commands to import data. And once again, Compose supports not only Altair solvers but also many others, as we have integrated all CAE reader capabilities from Hypergraph. And since CAE files are usually binary and not easily accessible with other programming languages or platforms, we can type read vector builder in the command window to launch the utility, then load the input file and check what's in there. And Compose recognizes all entities within this file: subcases, data types, requests, components, and time steps. Let's show with an example how to build the syntax to extract information from a crash simulation using read vector builder command. So like I just said, this file has information about a crash simulation. In this case, there are no subcases associated with the file. And as it's a dynamic analysis, we have different time steps, and I will select all time steps to be queried. Then we see that there is only one result type, which is angular acceleration. The requests that interest me from this crash analysis are the legs of the simulation dummy. Therefore, the request start is upper leg left, and the request end is the upper leg right. And finally, let's query the component that corresponds to the resultant angular acceleration. Once we selected the information that must be extracted, print button generates the syntax that will do the operation using the CAE functions that will be explained shortly. It may now be copied and pasted in your script and adapted if necessary. Now let's talk about read vector. Read vector is a function that reads test and CA files and returns a data vector. That is, the output has a single type of data. Let's see an example using read vector, how to access the CA file and use it to apply a filter on the data. As a good practice, it's good to clear Compose workspace up front. Then, declare the file name that we just showed in read vector builder example. And as we see here, read vector will read the given result type, which is angular acceleration, the request, which is lower torso, and the component, which is the resultant of angular acceleration. When we run the script, the output could be checked in the variable browser, and we will confirm that it's a vector. But before we run the script, let's review it thoroughly, and then we can go to the variable browser. Then let's plot the input data with dashed green line. Now, let's apply a moving average filter, which is simply a low-pass filter, given the polynomial coefficients to filter function. The filter data will be plotted in overlay with the input data. And finally, let's add a legend and labels to both axes with these commands here. When we run the script, we see both curves, the original angular acceleration of lower torso and the filtered result, and confirm the access to the CA result file. We also can confirm that the variable generated by read vector function is a vector containing a single type of data, which is information of all time steps of angular acceleration of the lower torso region coming from a crash simulation. Now, covering a bit about read mode vectors function, it extracts multiple types of information in a single command, such as several data types or several components at once, and therefore the output is a matrix. Instead of declaring multiple read vector commands, read mode vectors does the same job with less operations. Let's see an example using read mode vectors, how to access multiple requests from a crash simulation. So, using the previous file, let's now query not only crash results of angular acceleration in the lower torso, but also in the head. If we use read vector, it's not possible to get both results simultaneously, and that's why we would need one command for each request. Finally, let's plot both results, adding legend and labels of axes. On the other hand, if we do the same job with read mode vectors, we could query both requests with a single command and use the same functions as before to plot the two results, given their respective indices from the output matrix to plot each curve. When we run the script, we see both curves, angular acceleration of lower torso and angular acceleration of head, and we confirm the access to the CA result file. But let me remind you that two plots were generated and that they may be accessed through the project browser. The first one used two read vector commands, and the second one used one read mode vectors command. And although both plots are obviously the same because they query the same data, read mode vectors saves some time and reduces the size of the script because it extracts the same data with less operations. We are now about to explain our last read in today's video, which is readCAE. So, read vector and read mode vectors support arguments that could represent a single entity to be queried or a range of entities, given its start and end. But what if one wants to query a list of entities and not necessarily a range? To exemplify the situation, let's think about querying an entity list comprised by 1, 10, 15, 16, 17, and 30. These numbers could mean a list of channels in a test file or a list of elements in a CA file, for instance. Using read mode vectors, we would only give the start ID, which is 1 in this case, and the end ID, which is 30. And we'd be reading all information in between, and some of this information would not be useful. And that's why there is a third CA reader function called readCAE. The following example is how to access a list of requests from a crash simulation. Using the same file, let's now query results exclusively from lower torso and upper torso. If we launch Read Vector Builder to build a syntax to query these results, we see that the angular accelerations in the head are between these two, meaning that read mode vectors command would query all requests between the start, which is lower torso, and the end, the upper torso. In this situation, readCAE is more appropriate because we can explicitly give these two requests using a list format and not necessarily a range format. And coming back to the script, let's give the request start and request end to read mode vectors. On the other hand, readCAE supports a list which contains only what's supposed to be read. It means that the final matrix will not contain data between these two requests, saving computational time and memory to read these files. When we run the script, we see that, in fact, the variable created by read mode vectors function has a dimension equals to 3, which corresponds to lower torso, head, and upper torso information. Whereas the variable created by readCAE has the same dimension equals to 2, keeping data only about the lower torso and the upper torso. There are also support functions to get specific information of the input file if the user is interested in subcases, data types, requests, and components specifically. And we could retrieve not only numeric results per se, like we just showed in some examples, but also a list of subcases, names of the results, number of requests, and so on. Using these support functions, let's see an example how to get the maximum acceleration in respective region where it happens. Using the same crash simulation file, we go into query angular acceleration results based on the user's choice. After declaring the variables with the file name, result type, and component, we're going to get the list of requests using getRecList. As soon as it's stored in a variable, we may use it in listDLG function to generate a user-friendly dialog box which gives the user the possibility to select the requests. And as we are interested in the largest acceleration after the simulation is finished, let's get results based only on the final time step. We don't need to know which is the final time step up front, because we can use getTimeStepList function and AND operator to query the whole list of time steps and store only the final value. And now we are ready to use readCAE function to import angular acceleration results of the request selected by the user in the final time step of the analysis. Finally, with max function, we are able to get not only the maximum angular acceleration, but also the index and the request list where it occurs. With this index, we can get the request name with getRecName function. And the maximum acceleration value, the index in the request list where it occurs, and the request name are printed in the command window. Please visit Altair Forum, a place where users can interact, ask questions, exchange information, and post about model-based development.